Right now, at the bottom of the Mediterranean Sea, there are Roman harbors. Not ruins, not rubble. Intact harbors, breakwaters, piers, seawalls, 2,000 years old and still holding against the ocean. Your modern concrete? Engineers expect it to fail in decades, not millennia. So what exactly is happening here?
Here's the problem. Seawater is brutal on concrete. It seeps into tiny cracks. It attacks the steel hidden inside. The steel rusts, expands, and starts tearing the structure apart from within. That's why modern seawalls, harbors, and bridges all have a lifespan. Roman harbors had no steel, no rebar, no reinforcement at all. By modern logic, they should have failed long ago. Instead, they endured. For a long time, researchers thought the Romans simply built thick enough walls to survive. Then scientists from MIT and Berkeley drilled into ancient Roman breakwaters. What they found changed everything. The concrete wasn't just surviving, it was still changing. New crystals were growing inside the pores. Crystals that were never part of the original mix. The seawater wasn't destroying the concrete. It was helping build it. To understand why, researchers used advanced imaging tools to study the material at the microscopic level. Inside the ancient mortar, they found two key minerals forming over time. First came philipsite, filling pores inside the volcanic pumice. Then, over long periods, aluminous tobermorite began to form, creating interlocking plates and fine crystalline fibers throughout the structure. So every time seawater moved through a crack, it didn't simply damage the concrete. It triggered more mineral growth. The cracks were healing themselves. So, what gave Roman concrete this strange behavior? The answer begins with the material they chose. The Romans used volcanic ash from the Bay of Naples, known as pulvis putiolanus, mixed with lime and seawater. This ash was chemically rich in silica, alumina, and alkalis. When the Romans built their harbor walls inside wooden cofferdams and lowered them into the sea, the lime reacted strongly and gave off heat. The temperature rose sharply. Then the structure cooled very slowly over a long period. That combination of chemistry, heat, and time created the conditions for those rare minerals to form and keep growing for centuries. But the mystery didn't stop at the sea. What about Roman buildings on land? The Pantheon, the baths of Caracalla, structures that never touched seawater, yet still survive in remarkable condition. For years, archaeologists noticed bright white flecks inside Roman mortar. They assumed these were mistakes, incomplete mixing, poor workmanship, waste material left behind by careless builders. They were wrong. Those flecks were intentional. Roman engineers were doing something far more clever. Instead of pre-slaking their lime in water, they added raw quicklime directly into the dry volcanic mix. Then, water was introduced. The reaction was intense. Heat shot up rapidly inside the material. That extreme heat left behind tiny pockets of highly reactive calcium throughout the concrete. At
first glance, they looked like flaws. In reality, they were hidden reserves, built in on purpose. And that is where the real genius appears. When a crack formed, whether from an earthquake, settling, or age, water could seep into the fracture. It reached one of those lime pockets. The calcium dissolved into the water. Then, as conditions changed, it recrystallized as calcium carbonate. The crack sealed itself. No repair crew, no intervention. Just a concrete structure responding to damage on its own. Modern reproductions of this method can even seal very small cracks in weeks. For a while, scientists still wondered whether this was all intentional or just a fortunate accident. Then, Pompeii gave them the answer. Buried by the eruption of Vesuvius, an unfinished construction site was preserved almost exactly as it was left. The tools were there, the walls were half built, and on the scaffolding, archaeologists found piles of dry materials waiting to be mixed. Quicklime, volcanic ash, not random leftovers, a construction process frozen in time. Now step back and look at the bigger picture. Modern cement requires extremely high kiln temperatures. It also produces a major share of global carbon emissions. Roman concrete was made with far less energy. It cured differently. It lasted longer. And it did all of this without the steel reinforcement that makes modern concrete possible and also vulnerable. We didn't lose the idea because it was useless. We lost it because the world that supported it disappeared. The ash supply routes vanished. The empire collapsed. The need for huge harbors and monuments faded. So the knowledge survived only in fragments. Today, that old knowledge is being studied again for a very modern reason. Infrastructure everywhere is aging. Cities need materials that can last longer, use less carbon, and resist damage more intelligently. Roman concrete won't replace modern concrete in every situation, but it offers something valuable, a new way of thinking. Not a dead material, a living one, a material that can adapt, strengthen, and heal with time. And that may be the most remarkable lesson of all.